Okay, so what is going on now that we've done basics, it's kind of tedious to write all that stuff out. And we only did 3 rectangles. So when you did your area, if we wrote it generically, the area is, remember this is an approximation. It's not actually equal. The area is approximately equal to delta x, hang on, delta x f of x1 plus, this is actually 5.3 day 1. But I'm just still I'm on the warm up. I'm just writing something out for you to get set up the notes. x2 plus delta x, and we made our delta x the same for every single one, right? Well, section 5.3, is going to talk about, 5.2 is just area under a curve. And 5.3 is specifically talking about the Riemann sums. Hang on a second. They call 5.3 definite integrals. You know how what we did was an indefinite integral? I don't know if you remember me saying that. But it's getting in the more formal language of a Riemann sum. All right, so what it's going to do is going to take this, where we were just finding rectangles, and it's going to write it in more formal notation. Y'all did sequences and series and summation notation. Supposedly y'all dipped your toe in it last year, sort of. Okay, if we wanted to write this in a notation with summations, do we all agree? Areas approximately, if we do a summation and we say that our number of rectangles, we're going from 1 to 3, then delta x, and we're going to say n because it doesn't have to be all the same. We did ours all the same to make it easier to program, right? But it doesn't have to be. And then it's the f of x sub n that you choose. Is that a fast notation, mathematical notation for what we did?
Yes.
And that is the correct notation for when we're adding up a bunch of the same things. And Riemann sums is a perfect example of doing it. Because right now we're doing 2 or 3 or 4 rectangles, but if you've noticed, the area under the curve, our Riemann sums are going to match up to that actual area under the curve better if we add more rectangles, right? And if we do an infinite number of rectangles, are we essentially coloring underneath the curve? So if I took the limit of that as n goes to infinity, would I get the exact area? That's where we're going. But first, we have to learn the notation. We have to learn to do Riemann sums because Riemann sums are an approximation and the AP test loves it. So I want you to have the technique of finding Riemann sums now. And then we'll get into the whole, don't worry, by the end of the week we'll get to the limit notation. All right. So there's some things about summation notation that y'all need to understand that I don't know if y'all know yet. Y'all should have learned it last year, but y'all may not have, and you may not remember it. So, some things that you need to know. If you see summation notation, that's summation, by the way. That sigma, Greek letter, means summation. Okay, I like to use, we used n specifically for the number of rectangles, subintervals, divisions, right? And they use all sorts of words, but is it that number of rectangles, right? The other notation they use for summation, I learned I for iteration. So I was learning this notation so I could program. So I was the number, so as iteration, it was a for loop. We called them do loops. Y'all call them for loops. This is telling it the computer start at 1 and go to 4. Right? That's what that notation is saying. And if I say I want to sum I, it means I'm plugging in whatever step I'm at and then adding it to the next step. So in this case, if I is 1, it's going to be 1. Then I'm going to add 1 to it in the next step. So the next I is 2, and then 3, and then 4. That's what that notation means. you're going to do I in steps of 1, starting at whatever the I value is, going to the whatever's at the top of the summation. And then, what if it's I equals 1 to 4 for I squared? Oops.
1 squared plus 2 squared plus 2.
Yeah, exactly. It's going to be 1 squared plus 2 squared plus 3 squared plus 4 squared. So in this notation, the I is what is changing, and it can talk about the first x, the first function value, whatever it's going to be, or I itself. If it doesn't have an I, then it's not changing in the iterations. So for example, if I do summation of I equals 1 to 4, sorry, that's a really messy 4. I'm trying to make it still a little big wiggy. Suppose it's some constant. Is it going to be the constant plus the constant plus the constant plus the constant? Because the value isn't affected by I. It's just telling you to do it that many times. For instance, if I say sum I equals 1 to 4, 2, does that mean add up 2 4 times? My function's 2. Is that okay, remember when we were doing the velocity? If my velocity was 60 and I say do that 4 times, is that in 4 hours? So that's 240 miles. That's what this is saying to do. It's saying 2 plus 2 plus 2 plus 2 equals 8. And the other thing is, what if I say I equals 1 to 4 of C sub I? That means C is dependent on I. We don't know what it is, but is that going to be whatever C1 is, C2 plus C3 plus C4? Is that like our X's? Our X1, X2, X3, X4? Yeah, it's just like that. Same concept. Okay, so when we look at our warm-up, from our warm-up, right, we can be very specific. So this is for our warm-up. What was our delta x?
1/2.
1/2, right? So the area was approximately the summation. How many subintervals did we do? 3, right? And then it would be our function value at whatever x was for the first rectangle and the second rectangle and the third rectangle, right? The rectangle number is the I, is the iteration number. And then our delta x was 1/2 every single time, so it's just times 1/2. Is that another way of writing that notation that we did?
Yep.
Yep, it is. But here's the tricky part. The x's aren't, how to find the x's. So that's what we're going to work on now. Because by the time we finish, we're going to have this very specific to our problem, so we can go backwards and forwards from the word statement to this, because this doesn't include our interval, right? There's some information missing. So I'm going to show you how to get all of it, because what are they going to do on the AP test? They're going to give you the summation notation, ask you to write an integral, which is what that word statement was. We're going to start with baby steps. We'll get eventually to where we're writing integrals. Okay, so I'm going to go to a new page. We're going to draw a little sketch first, so before we finish up. So in this sketch, and we're going to do a different problem. No, actually, let's go ahead and finish up the warm-up. For our warm-up, specifically, was our f of x equal to 9 minus x squared?
Yep.
And our interval was 0 to 3/2, right?
Mm-hmm.
So to get delta x, was it b, which is 3/2, minus 0 over 2. Just write that down. That's our b, that's our over 3. It's over 3, right?
Yeah.
All right. So if we looked at the bottom of our curve, for our right-hand sum, so we had 1, 2, 3 rectangles, right? Was this our first x? Oh, sorry, wrote the wrong place. Is that our first x, and this was our second x, and this was our third x for the right-hand sum? Now, we need to define those x's. We need to use where we start. Did we start at 0? So our a is equal to 0. Does everybody agree?
Yes.
For the first rectangle, do we go a plus delta x? So for every single time, our x sub I is going to be the a plus the, delta x. It's a delta x. The delta x, in our case, we're not going to put an I there because our delta x's are all the same, times I, right? For the first rectangle, do I add 1 delta x?
Yep.
To get the second x, is it a plus 2 delta x's? And for the third, is it a plus 3 delta x's? So is this a generic formula that's going to give me how to find x based on the iterations in our delta x? That's going to go in that formula. So you know how we ended up with a is approximately summation of I equals 1 to 3 of f of x? We know what f of x is. We can now go, it's 9 minus, well, do we know what our delta x is? It was a half, right? So it's going to be 9 minus, so for each one of these delta x's, this, for our generic one, so ours is going to be x of I equals 0. That's generic. Ours is actually going to be plus 1/2 times I. So is that just I over 2? So it's just going to be, can we get rid of the 0? So it's going to be I over 2 squared times 1/2. And that tells you everything you need to know. So if you see this summation, you know that the function was 9 minus x squared. The delta x was a half. You started at 0, right? And you're going to end up at 3/2. Here's how you know. This has to be a plus delta x I, which means it has to be 0 plus 1/2 times I. The only way to get this thing that's squared in here, because the x has the I in it. The x of I, it has an I in it. So that's how you're going to know where the x is. And since there's nothing there, it has to be a 0. That is the hardest one. Whenever a is anything else, so if I started a at 1, this would be 1 plus I over 2. And that one's easy. It's the one when it's a is 0, that's one y'all can't see. We're not going to do this in the assignment today, but we will get there by Friday. Okay, so now we're going to write the generic one for all of them. So I'm going to say, so this is the generic for any Riemann sum, what the summation notation is going to look like. We're going to pick 4 subintervals so you can see how this works. I'm just doing the bottom. 1, 2, 3, 4 rectangles. Yeah? So for some f of x. It's still wiring a little weird. And we're going to say this is the a and this is the b. And our delta x is equal to b minus a over the number of rectangles. In this case, it's 4. Over 4. Right? All the delta x's are the same. So we're going to start with the right hand. Here's our right hand sum. We're not going to use a. For our first one, we're going to go down. This is x1. This is x2, and this is x3, and this is x4. Agreed? Everybody see that? Then for our left hand, a is going to be the x1. We're going to start here. x1, x2, x3, x4, and we're done. And for the midpoint, do we have to go halfway between? x1, x2, x3, and x4. when we go to find the delta x, I mean the actual, to write this x, we want to write a formula for our computer where it finds the x1, x2, x3, and x4 for us. So for right hand, for the x sub I, oh, by the way, I like I for iteration, but apparently the latest and greatest now, for our textbook, it uses K. And believe it or not, I, J, K are the note letters. I laughed every time I saw that. I, J, K. Those are the letters they use for iterations. So on the AP test, it could be an I, it could be a J, and it could be a K. Huh?
The Bose factoring.
Yes. Okay, so I equals, we have to include A, and then we just said it was plus delta x times I, right?
Mm-hmm.
Well, if we're doing left hand, do we want a delta x to begin with? Do we want to add a delta x? No. But we need to include the A. We're always starting in from A. But this time we're only going to add a delta x after the first rectangle. So I'm going to do x minus 1. Oh, sorry. Right? And our I, we're going to say, well, this, I'm saying I here, but our delta x's are all the same, right? So for the first rectangle, I'm using A, I'm using left-hand side. I don't add a delta x. That's why it's I minus 1. So am I going to add a delta x for the second rectangle? I'm going to add 2 delta x's for the third rectangle. Does everybody see how you get to the delta x's, right? To get to the third x for a left-hand sum, do I have to add 2 delta x's? And then for the midpoint, I'm going to add half a delta x. So it's x sub I equals a plus I minus 1/2 delta x sub I. And we're done. That's all I was going to show you.
Oh, shit, that's us, bro?